Hey there, STEM chemistry students. This is Miss Ruark, and this is podcast 7.4, where we're going to be talking about ideal gases and the difference between an ideal gas and a real gas, because there is a difference. All right. So, an ideal gas. There's an ideal gas law that incorporates all the four possible variables that we could use when we're talking about gases: pressure, volume, number of moles, and temperature in Kelvin. Well, with this ideal gas law, remember we have pressure, we have volume, we have the number of moles, and we have the temperature in Kelvin. And we can take this whole thing and we can set it equal to a constant, right? Well, this constant in this case here is actually going to be R. And R is our ideal gas constant. And so our equation that we use is called, it's the ideal gas law, PV is equal to nRT. And I will probably refer to this as PivNert, just because it's easier that way. Anyway, so with PivNert, it is an ideal gas law equation. It's used to describe the condition of a gas as it is now. The combined gas law or any of the individual gas laws will be used to predict what the gas will become or what conditions will change to if you change one or more of the conditions. Okay, so if we were to if we had an initial and a final set of conditions, we would use the combined gas law. If we only have one set of conditions and we're looking for something that, one of those variables that's missing, we'll use the ideal gas law. And you need to be able to differentiate between the two. Okay. So I guess we're just going to jump right on in on this. Actually, I do need to give you just a little bit more information. The values for R. R has a couple different values depending on what units you're using. All right, so if you have your pressure set in kPa, then the value of R will be 8.31, and then your units would be liters times kPa divided by moles times Kelvin, all right, because R is equal to PV over NT. All right, well, what if we had our pressure in units of atmosphere? Well, if we had our pressure in units of atmosphere, we would do 0.0821 liters times ATM over moles times Kelvin. All right, and we could have, excuse me, we could also have our pressure in torricellis or in millimeters mercury, but honestly, you can go ahead and change. It's a really easy conversion to change and end up using one of these two. So I'm just going to give you these two. That way you don't have to memorize more. Pick the one that you like the best and use it if you need to, and then you can just do your conversions to get your pressure and all your other units to match up. Okay. So let's jump in. Example problem 1, it says how many kilograms, so we're looking for kilograms of methane gas, are in 225 liters, that would be our volume, of a container at 150 kilopascals, that's our pressure, and 35 degrees Celsius, which is our temperature. Okay, so we know that volume is equal to 225 liters, pressure is equal to 150 kilopascals, and our temperature is equal to 35 degrees Celsius. And they want to know how many kilograms. Okay, now we know we only have one set of conditions, so we're going to use PivNert. The problem is we don't have kilograms in this thing. Okay, we do have pressure here, volume matches up, we have temperature, which we need to change to Kelvin, so we add 273, right, and 35 plus 273 gives us 308. We know R is our gas constant, so we must be solving for N in this one, and N stands for moles. Can we go from moles to kilograms? Sure we can. All right, so now all we have to do is plug it in there. Just plug and chug, right? Okay, so P is 150 kPa. We multiply that by 225 liters. N we said we're solving for. R is going to be, we have kPa for our units, so 8.31 liters times kPa over moles times Kelvin. And then our temperature is 308 Kelvin. Okay, now you can cross out your units now, or you can do it at the end. I don't care which one you do, just as long as you make sure you keep track of your units. All right, so I'm going to go ahead and cross mine out now because I know that these are all going to cancel. and I'm left with moles. All right, so get N by itself, divide both sides, do your math, blah, blah, blah. Okay. I'm not going to actually write it all out, but I'm going to, just in case there's anybody who says, how did you get that number? We're going to divide both sides by that number here, so that way they cancel. Those divided there, N is going to be equal to 13.18627, and there's more, moles of methane. But we need grams of methane. So we've got to multiply by 1 mole on bottom, and on top we need 16.05 grams of methane. And when we do that, the calculator gives us 211.6396 grams of methane. But we don't want grams, we want kilograms, right? There's 1,000 grams in 1 kilogram, and so it gives us 0.21163, but we only want how many significant figures? There's 3 here, there's 2 there, so we want 2 significant figures, 0.21 kilograms of methane, and there's our answer. All right. Not too shabby. We just learned a new equation and plugged in the rest of it. We already know all this stuff, so this is pretty easy, right? Sure it is. All right, question number 2 says, find the number of grams of CO2 that exert a pressure, so we're looking for grams, that exert a pressure of 785 torr, and it has a volume of 32.5 liters at a temperature of 32 degrees Celsius. Okay, so pressure is equal to 785 torr. Our volume is 32.5 liters, and our temperature is equal to 32 degrees Celsius. Let's go ahead and change that into Kelvin. 32 plus 273 gives us 305. All right, we're looking for grams, which means we have to solve for N. Our pressure units are in torr, so we need to change that. Now, I think it's the easiest one to change is to go to 1 atmosphere, because it gives us a 1 in our numerator or denominator, so it's less math that we have to do. So 785 divided by 760, 1.03289 ATM. Okay. So now we just plug into PV and RT, and we do 1.03 ATM times 32.5 liters is equal to N times, now we've got ATM as our pressure unit. So this time we're going to use 0.0821 as our R value. And then 305 Kelvin. Okay. Units cancel, units. We're left with moles. So the math, when we do the math, it tells us that we have 1.336834 moles of carbon dioxide. But we don't want moles, we want grams, so we have to do a mole conversion. So 1 mole of carbon dioxide is equal to 44.01 grams of carbon dioxide. Do the math, and the calculator gives us 58.83, and there's more numbers, grams of CO2, but we don't need more numbers because we just need 3 significant figures. So 58.8 grams of carbon dioxide. There we go. All right, let's do another one. This one says if the density of a gas is 1.2 grams per liter at 745 torr and 20 degrees Celsius, what is its molecular mass? Okay, so now we're looking for, and I'm going to write big M, molecular mass. Okay. We know that it has a density, what? And it has a pressure, and it has a temperature, right? Well, density is equal to mass divided by volume. Okay, so mass divided by volume means we're going to have a mass measurement on top and a volume measurement on bottom. Well, the nice thing about this, PV is equal to nRT. Let me show you something real quick. PV equal to nRT. This N here, we can figure out the number of moles of something by taking the grams or the mass of that substance and dividing it by its molar mass, right? If we take grams or mass divided by molar mass, that'll give us the number of moles. So mass divided by molar mass. All right, well, we can plug that in for N. If we plug that in, PV would be equal to mass over molar mass times RT. All right. Well, we need to get density, and we know that density is mass divided by volume. So can I take this and divide both sides by that? Sure. If I divide both sides by V, that leaves me with P is equal to mass over molar mass times RT divided by V. And you're like, Ms. Rick, it still doesn't make any sense. Well, let's make sure that these denominators come together. So P is equal to M RT, mass times R times temperature, over the volume times the molar mass. Okay. Oh, look, there's density. So we can just plug in density there, right? All right, so P is equal to density times R times T over molecular mass, or molar mass, same thing. All right, so we can actually use this equation. All I did was I derived it just now by plugging in things that we already know. So we can use this equation right here to solve for our molecular mass. We know that the density is equal to 1.2 grams per liter. We know that our pressure is equal to 745 torr. We'll need to change that. And we know that our temperature is equal to 20 degrees Celsius. Well, if we add 273 to that, we get 293 Kelvin. And then if we change times 1 atmosphere over 760, we end up with 0.980 atm. Okay, so now we have our density, we have our pressure, we have our temperature, and we have our R values, so we can plug into this and solve for molecular mass, right? We can also rearrange this so that it would become molecular mass is equal to D, density, times R times T over P. Makes it way easier so we don't have to really do any extra moving, right? Okay, so let's plug this in here. So molecular mass is going to be equal to 1.2 grams per liter times our R value. ATM is our units, so 0.0821 ATM times L over mole times Kelvin, and 293 Kelvin. And then we divide that by our pressure. Our pressure is 0.980 ATM. Right, our units are going to cancel, kelvins, kelvins, liters, liters, and we're left with grams per mole. Okay, so when we do the math, we end up with 29.455 grams per mole, which is molar mass or molecular mass, and we only want two significant figures, so 29 grams per mole would be our answer. All right, not too bad. Okay, so what's the difference between an ideal gas and a real gas? Well, ideal gases follow gas laws at all temperatures and pressures, conform to all assumptions of the kinetic molecular theory. We assume the particles have no volume. There's no intermolecular forces that are tracked between those particles, and guess what? They don't really exist. All right. So real gases, we have to factor in particle volume. We have to look at the attractive forces between the particles. They differ mostly at low temperatures and high pressures, and real gases are a true picture of what the gases do. So since no gases are really ideal gases, they come close to behaving like an ideal gas at low pressure and a high temperature. And so that's why we use the ideal gas law to help us predict the behavior of these at low pressures and high temperatures. All right, so we can do gas mixtures, and the reason for that is we take it and go into this because with gas mixtures, we're using real gases. So we have partial pressures of gases, which is the individual pressure of the gas in the mixture. And Dalton's law of partial pressure says that for a mixture, the total pressure is equal to the sum of the partial pressures of all the gases in a mixture. Okay. That's pretty easy, right? Okay, so let's do an example here, and I might run out of time, so if I do, I'll just do a part B on this. All right, we have a 250 milliliter sample of oxygen collected over water at 25 degrees Celsius and 760 millimeters mercury pressure. It says, what's the pressure of the dry gas alone, knowing that the vapor pressure of water at this temperature is equal to this pressure? Well, we know that the total pressure is equal to the pressure of 1 plus the pressure of 2. The total pressure here is 760 millimeters mercury. And we know that the pressure of the water vapor is 23.8 millimeters mercury. And we're just looking for the pressure of the gas alone. Okay, so I'm going to finish this up on part B, which won't take very long. Okay. See you in a few.